The last question is one that is worth knowing just in case it pops up in biochem or maybe biology, but it's a question of what do transition states look like? And I missed the S on state here, but what do transition states look like? And this has to do with Hammond's postulate. So the question, what do transition states look like, has two different versions, right? One is, what do transition states look like on an energy coordinate? Okay, so transition states are at the top of these energy profiles, these hills, all right? So the very crest of the hill is the transition state for each of these individual pathways, all right? So the red line and the pink line, these are the lines that compare the relative energies of the transition states of these two pathways, these pairs of pathways, all right? So you should be able to recognize where transition states happen on a reaction coordinate relatively easily. The second version of what do transition states look like is what do their actual structures look like? What do you draw as a picture form of a transition state? Well, the reality is that you cannot isolate transition states. We cannot prove what transition states look like, okay? But Hammond's postulate gives us a way of thinking about the structures, the possible structures of transition states, and thinking about how it affects reactions. So here is our before and after image or picture of starting materials, if you will, and products, but it's really starting intermediate and ending intermediate. To start off with, we have a halogen radical and our neutral covalent hydrocarbon structure, and after we have our HX and we have a new radical, a new intermediate, that is a carbon radical, right? So the question is, what happens in the middle? What does the middle look like? And so you could write it like this, and I say middle with a question mark because, again, we don't actually know. What we do know, based on where we started and where we end, is that we know that the HX bond has to form, and we know that the CH bond has to break. Okay, so we draw dotted lines and make them a little bit longer because longer bonds are weaker. Obviously, a dotted line is less solid than a solid line. And so, you know, these bonds look weak, and they're supposed to look weak. They're essentially a half bond on each side. All right, and again, this doesn't really represent anything in particular. It's just a visual representation of what's happening. One bond is forming, so it's not quite full, so it's dotted. The other is breaking, so it's not quite full, so it's dotted. Okay, this double cross right here represents, it just means transition state, okay? And it tells us that we don't actually think that this is something that we can isolate experimentally. And we also have this radical shown here because we know we start with a radical and we end with a radical. So we know there's a radical involved, but as this is happening, we don't know where that electron is. And so we just say, well, it's somewhere on here, and that's what the brackets mean. Okay, so somewhere in this bracketed species, there's a radical floating around doing something, we think. Okay, so I put the question mark there because, you know, is this what this looks like? We don't know. Hammond's postulate, which you've probably already read, just states that related species that are closer in energy are also closer in structure. So the structure of a transition state resembles the structure of the closest in energy, stable species or local minimum. Okay? So here's the combined reaction coordinate diagram that I've put together. And what you'll notice is, you know, this reaction this is starting material, this is product, all right? For this reaction, this is starting material, this is product. So we have starting materials on the left, all right, products on the right, just like any reaction coordinate, all right? But you'll notice that our hills, which are in the middle of the reaction, right, they aren't drawn on this line. So here I've just put this silver line in between our starting material and product energy levels on our, you know, our x-axis, our reaction axis, all right? So there's a reason that these crests of these hills don't live on the center in between products and starting materials, okay? And it's because of Hammond's postulate. Okay, so if we look at the transition states for the chlorination step, so these two transition states, okay, obviously the energy level here and here is significantly smaller than the energy difference between here and here, okay? And so Hammond's postulate states that because these transition states are closer in energy to the starting material being with hydrogen attached to carbon, it means that the transition state is going to look more reminiscent of that. So this is why the hydrogen is drawn closer to carbon than to chlorine. All right, we still have our double cross for transition state is still a radical. All right, but that's why it's drawn like that. This is also called an early transition state. Again, I don't know if this is going to pop up in biochemistry or not, but just in case it does, this is called an early transition state because the transition state looks like the earlier part of the reaction. Okay? For the bromination step, the same thing applies. All right? So we have our transition states here and we have our transition states here. Okay? So in this case, what are these transition states closer to? Okay? The energy difference between this, okay, and this is significantly smaller than the energy difference between this or this. All right? So the transition states are much closer to the products. And since they're much closer to the products, that means that the transition state, according to Hammond's postulate, resembles products more than starting materials, and that's why in this case you have the hydrogen more closely bound to the bromine, where it is attached in the product, than to the carbon. All right? And not surprisingly, this is called a late transition state, again, because the transition state resembles the later intermediate in the reaction because it's closer in energy. And so if a reaction is exothermic, you always have an early transition state. If a reaction is endothermic, you always have a late transition state. Okay? And so because of Hammond's postulate, this is why we draw endothermic transition states on the right side of this line instead of right in the middle. All right, and with exothermic, we always draw the transition state on the left side of this line, again because it's closer to the starting materials in terms of energy, and according to Hammond's postulate, in terms of structure. All right, so yeah, that pretty much covers everything about chapter 4. It's a lot of information, so again, if you have questions, please ask. Thanks.